Hey Global Impact, this is Mr. Ellinger here. Today's lesson is on real numbers in the number line. Two learning targets for this unit. We want to be able to classify, graph, and compare real numbers. We also want to be able to find and estimate square roots. Some essential understanding for you in this lesson. First, the definition of a square root can be used to find the exact square roots of some non-negative numbers. The square roots of other non-negative numbers can be approximated. Numbers can be classified by their characteristics. Some types of numbers can be represented on the number line. Some background for this lesson. As you've studied mathematics, the inventory of numbers that you've worked with has expanded, starting with natural numbers, the counting numbers, then whole numbers, then positive rational numbers, fractions, all the rational numbers, and then finally the entire set of real numbers. And we have the negatives in there. As a number line is examined, it can be seen that each of these subsets of real numbers, meaning smaller sets, can be shown as distinct points on the number line. However, there are numbers that can exist between each number that can be shown. For example, there exist infinitely many numbers between 3 and 4. Think about that for a minute. Between the numbers 3 and 4, there are an infinite amount of numbers. There exists infinitely many numbers between 3 and 3.1. There also exists infinitely many numbers between 3 and 3.0000001. Now 3 and 3.0000001 are very close together, but there still exists an infinite amount of numbers between those two numbers. And we could continue on like that forever. Understanding this concept may help in preparation to comprehend the concept of irrational numbers, and will eventually lead to a discussion on imaginary and complex numbers in more advanced courses. This also gives you a preview of concept in calculus. So the first question is, what is a square root? Well, here's a kind of a definition. A number a, some number a, is a square root of a number b if a squared equals b. There's an example. 7 squared equals 49. We know that. So we say 7 is a square root of 49. Another way to think about a square root is what number times itself equals some given number. So take for instance this expression here. That's asking us, what is the square root of 36? The radical symbol indicates a non-negative square root, also called a principal square root. The expression under the radical symbol is called the radicand. The whole thing, square root of 36, is called a radical. It is read radical 36, and it's asking to calculate the positive square root of 36. The word simplify, remember, means do any calculations that you can. It's kind of like reducing a fraction to lowest terms. So radical 64 is asking us, what is the square root of 64? What number times itself equals 64? 64 is one of those numbers that we call a perfect square number. It has a whole number square root. A lot of times we remember like 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64. So the square root of 64 is 8. Here we have a fraction. Radical 1 over 36. If you remember back to our last lesson, anytime we had a fraction to a power, we had to figure out what we had to multiply the numerator by itself however many times and the denominator. Well, this is kind of the same thing. We need to look at what is the square root of 1 and what is the square root of 36. And we will put that answer into a fraction. Well, the square root of 1 is 1 times, and the square root of 36 is 6. So the answer to this problem is 1 over 6. In the last lesson we said we don't want to use calculators. If you try to use a calculator for this, you'll get some funky answer. Thinking about perfect square numbers some more, here we have another fraction. We just need to think about these two numbers, 81 and 121, if they are in fact perfect square numbers, and they are. The square root of 81 is 9, and the square root of 121 is 11. So we can estimate a square root, give an approximate answer when an exact answer is not possible. So what is radical 34 to the nearest integer? Well, this is where our knowledge of the perfect square numbers is going to come in handy. All right, so we're looking for the square root of 34. Well, we know that 3 squared is 9, 4 squared is 16, 5 squared is 25, and 6 squared is 36. So radical 34 is going to fall somewhere in this gap. 34 is very close to 36. So the square root of 34 is going to be very close to 6. Since the problem asks us what is radical 34 to the nearest integer, that's a positive or negative whole number, we're going to go with 6. So the answer to this problem would be 6. Now, classifications of numbers. We have different number sets. A set is a well-defined collection of items. Each item in a set is called an element of the set. So we have what are called the natural numbers. They're the counting numbers. So here we have the natural numbers presented as a set in set notation. We'll address that in a second. And then those natural numbers graphed on a number line. A dot on 1, a dot on 2, a dot on 3. We also have the whole numbers. The whole numbers are almost identical to the natural numbers. They just include the number 0. The integers take the whole numbers and then take all the negatives of those whole numbers, throw them into a set with the positives, and you have the integers. So not only do we have 0, 1, 2, 3, but we also have -1, -2, -3, and so on and so on and so on. So a couple questions about this. How many items are in each set? These 3 dots here, which is called the ellipsis, tell us that this set goes on forever. The integers actually goes on forever in 2 directions, in the positive direction and the negative direction. So there are an infinite amount of numbers in each set. So some more classifications of numbers. We also have what are called rational numbers. A rational number is any number that you can write in the form a over b, where a and b are integers and b does not equal 0. We can't have 0 in the bottom of a fraction. It's what's called an undefined value. A rational number in decimal form is either a terminating decimal, such as 5.45, or a repeating decimal, such as 0.41666, ... again, on and so on and so on to infinity. We can write that as 0.416 with the bar over 6, implying that the 6 repeats. An irrational number cannot be represented as the quotient of 2 integers, meaning we can't write it as a fraction. In decimal form, irrational numbers do not terminate or repeat, meaning they're an infinite, non-repeating decimal. So there's a couple of examples for you. 0.101001001, and so on and so on and so on, in no pattern. And then pi. Pi is what's called an irrational number. Some square roots are rational numbers and some are irrational numbers. If a whole number is not a perfect square, its square root is irrational. So here we have some rational square root examples. Square root of 4 is 2. Square root of 25 is 5. Some irrational ones. Square root of 3. Square root of 10. Where are these elements on a number line? Between 0 and 1 here, we know that there are an infinite amount of numbers in here. Some are rational, some are irrational, but there's an infinite amount of numbers here. Another thing we want to examine in this lesson are what are called inequalities. An inequality is a mathematical sentence that compares the values of 2 expressions using an inequality symbol. So not equal. So we have the less than symbol, we have the greater than symbol, we have the less than or equal to symbol, and we have the greater than or equal to symbol. So one thing that we might be asked to do is write an inequality that compares the numbers radical 129 and 11.52. Which one's bigger? It might actually be to our benefit to use a calculator on this one, because radical 129 is not something that is readily obvious to us. So the square root of 129 is 11.36 to the nearest hundredth. And then we have 11.52. See, these 2 numbers that they gave us, those are not 2 numbers that are in the same form. If we use a calculator, go ahead and get the value of the approximate value of radical 129 in decimal form, then we can compare these 2. When numbers are in the same form, and really decimal form, it's fairly easy to compare them. When they're in this form, 11.52 is clearly larger than 11.36. So this statement says that 11.36 is less than 11.52. That's how it would read. From that we could infer that 11.52 is greater than 11.36, so we could also write this statement. Both are correct.